Welcome everybody to this seminar about the interpretation of convolutional neural networks through decision trees. You can find this paper on the bottom of these slides. This method is within the global post-hoc explanation method. It is obviously from the title a model-specific method for convolutional neural networks. It is thought for image data, and in this paper it is used in an image classification task, but it can be used also in other ones. Convolutional neural networks are a kind of architecture for neural networks, and they are thought mainly for images. If you want more information about the CNNs, you can find at the bottom of the slides. However, the main components are the input image or the input from the previous layer, which is the blue one in this GIF, and the kernel or the filter, that is the green one, that slides over the image and produce the feature map. These are the main ingredients for our method. This method goes beyond the pixel level visualization of CNNs, such as GradCam and visualization filters, and indeed it constructs an explanatory tree, and the method is able to quantitatively explain which filters and parts are activated and contributed to the prediction of the CNN. So the first task in order to arrive to build our decision tree is this. We have to bridge the middle layer features with the semantic concept. This means that we have to associate its neural activation inside the CNN with the semantic concept, and we need to force feature representations in middle conv layers to be well disentangled during the learning process. This means that each filters need to be activated by the same object region over different input images. This is done in this work without the use of any annotations of parts or textures to supervise the disentanglement of filter features, and this is a great thing. The second task after the disentanglement of the features is this. We have to assign the middle layer features with the specific part concept, and the next issue is to quantitatively explain how the CNN use these middle features to compute prediction scores. We want so to clarify for an input image the specific rationale of the CNN prediction. But what is a rationale? We have Wizard Merlin to help us. We define the rationale of CNN prediction as the set of part of the object parts or filters, because they are connected, that are activated and contribute to the prediction. So let's do a summary of the method. We have a pre-trained CNN. We propose the method to construct a decision tree to explain CNN predictions semantically and quantitatively. We summarize rationales of the CNN prediction on all images into various decision modes. Each tree node of the built decision tree represents a decision mode. Each decision mode describes common rationales of predictions that are shared by multiple images. This means that for these images, the CNN usually activates the same filters, or this means the same object parts in the input image. The decision tree hierarchically represents all potential decision modes of a CNN in cohorts to find manner, and this means that the nodes near to the tree root node mainly represent most common decision modes, and nodes near leaves correspond to fine-grained modes for a minority of images, until the extreme, that is the leaf node, that encodes the specific decision mode for just one single image. Then there is the inference phase. At the end of our method, when we built the decision tree, we have this phase where we infer from the decision tree a parse tree to encode a series of explanation. Each node quantitatively explains the prediction, okay, at the different abstraction level, and in other words, it clarifies how much each filter, object part, and input image contributes to the prediction score. So now let's start with the first task, that is learning disentangled features. Ordinary filters are those on the left of this image, and so they are activated by different object parts in the input image. What we want to reach is the disentangled filters on the right of this image. As we can observe, the filter 1 is activated just by the head, by this single part, object part in the input image, and as well as the filter 2 and filter 3. This is done in an unsupervised way. We expect the filter to be automatically converged to the representation of a part. This is done thanks to a special loss for the top conv layer. This loss can be found in this other paper, that is Interpretable Convolutional Neural Network by Zhang et al. And let's define some taxonomy for this loss function. So let XF be the feature map with dimensions L per L, and we can summarize the filter loss as the minus of the mutual information between the distribution of the feature maps and the depth of part locations. In general, mutual information quantifies the amount of information obtained about one random variable by observing the other random variable. So we have this loss here, and let's take the laser pointer. This is we have to minimize this minus mutual information. That means that we have to maximize the mutual information that is given by this big formula. In this formula, we have this information. We had XF, big XF, that is the set of feature maps of F extracted from different input images. We have the set P of all part location candidates, that is composed by two numbers actually, no? By one H, well, by H and W that spread between 1 and the dimension L of the feature map. Each location is given by these two numbers, mu, H and W, and we have also the empty set belonging to P, because this denotes the case in the target path does not appear in the input image. Finally, we have the joint probability P XF given mu that describes the compatibility between XF and mu. But now that we have disentangled features, we have to go to the second task, and now we have to quantitatively estimate the CNN prediction, how the filters contribute to the different prediction. So we are interested more in the high conv layers, as we will see, because these are more prone to represent object parts, while those in low conv layers usually describe textures. Moreover, we are interested in the top three layer of our decision tree, because these this layer, the second three layer, for example, describes more images with respect to the leaf nodes, as we said, represents just encodes just what decision mode for just one image. So some taxonomy for our algorithm. We have X belonging to RL per D, that denotes the feature map with a scale of the feature map, and D, that is the number of filters. Y denotes the scalar classification score of a certain category before the softmax operation, and the EXHWD, that is a scalar, denotes the element at the location HW of the fifth channel. The corresponding G weight describes the importance of XHWD for the prediction image I. The weights G denote a specific rational of the prediction for the input image. G per X measures the X quantitative contribution to the prediction. These two quantity can be put inside this equation, and from this we can also go to another form that is more familiar, that is this one. From this equation we can compute the vectors x and y belonging to Rt as an approximation of the tensor to the tensor x and the partial derivative of y with respect to x. I do not enter in the equations to compute x and g, but the most important thing from this equation 3, the Mickey Mouse equation, is that we can compute the x and gi. Now let's go to learn the decision tree. The most important thing for this paper is that we have to learn a decision tree to interpret the classification of each category. So from now on we can focus on the decision tree for a certain category, which this means, for example, for the mixed dataset that we concentrate just for the prediction of for a certain input image, for the prediction of 0, for the prediction 1, and etc. So some taxonomy. We focus on a certain category, as we said. The images belonging to this category are the positive images, and the other ones are the negative images. Omega plus denotes the indexes of the positive images, and omega is the whole training image. Yi denotes the classification score for the target category before the softmax layer. Its node V in the decision tree encodes the decision mode. Okay? Let's go. Thanks always to Wizard Merlin, we can define better what is a decision mode. A decision mode represents a common rational of the predictions shared by a subset of positive training images, omega v subset of omega plus. So how we can interpret the decision tree once we built? We have this decision tree, and we have a hierarchical encoding of the decision modes, and the children nodes V prime belonging to the childhood of V divides the decision mode of the parent V into fine-grained modes. Some other questions that are quite important. We define for each decision image, the decision mode is given by the first equation. That is given by W transpose per xi plus b. W is defined as alpha element-wise multiplication g hat. Alpha is given by a selection of filters, and it's a binary filter, okay, with dimension the number of filter d. For the leaf node, alpha will be once, and W, so therefore, will be gi. Gi is computed in the equation 3, the Mickey Mouse equation. So now we have defined the decision modes. What is g hat? G hat is obtained from the maximization of the cosine similarity of gi and g hat. So g hat represents the common rational for all the gi, and gi are all the weights for the input images belonging to the omega v. So for the images represented by the node that we chose in the decision tree. So in this way we can compute g hat. In this other way, by the equation 6 of the Ursula equations, we can obtain alpha and b by minimizing these quantities. What is the meaning of this equation? This is as we can observe, the first part of this equation is the decision modes. It is here defined. And his is yi, the target prediction. The prediction score for the target category of our CNN. So we want to minimize the distance between our decision modes, our estimation of decision modes, and the real score of the CNN. Let's go inside the algorithm. So we have to learn a decision tree for each category. In input we have a CNN with disentangled filters thanks to the first task, and we have the training images omega dividing omega plus and omega minus. In output we have obviously a decision tree. We initialize the tree Q with P0, the initial with just a root node, and P equal to 0, which will be increased during the learning algorithm, the learning phase. So now we have the initialization phase. For each image II, with I belonging to omega plus, we initialize the child of the root of the initial tree Q by setting G hat equal to Gi, because as we said, alpha is equal to 1 for the leaves node. Gi is computed by the equation, Maleficent equation, or Mickey Mouse equation in the simplified form, as that we have already encountered. Now, this starts the learning phase. Here it starts. So we go on until we have delta log E minus or equal to 0. But what is E? So E is defined by this equation here, and it computes at the denominator P dxi denotes the likelihood of xi being positive with the estimation using the 3p. At the denominator we have the same amount, but the likelihood is computed using the 3q, so the initial tree, and this represents the discrimination power. This is instead just a sparsity of the decision mode. It is not so useful and important. So the objective is penalizing the decrease of the discriminative power and forces the system to summarize a few generic decision modes for the explanation. And so, step 1, we choose the V and V prime, the second tree layer of the previous tree, that maximize the delta based on equation here. And then, once we chose V and V prime, we generate a new node U based on the equation 5 and 6 that are this one. And in this way we obtain the tree PT. So let's see this in a visual form. We choose V and V prime that maximize delta log E. We add then V and V prime to a new node U, and we have a new tree. Then the same thing is done with a new tree, where we choose another two nodes V and V prime and are added to another node U, and so on. At the end, we reached our target when we just to label the matrix A. That is a method that assigns filters with a semantic object. We will see this better later. So now we have to interpret the CNNs, and in fact we are in the inference phase. We can infer parse tree, which starts from the decision root node, and we select the decision modes in node U as the rational. So we can further select its child V hat that maximize the compatibility with the most specific rational GI. What does this mean? This means that once we chose a node U, we select the best child V that maximize the cosine similarity between GI and the weight of the decision modes of the node V. At the end, we can arrive some nice visualization, such as the pie chart, where we can say, for example, head, the object part head in the input maze contributes 93%, the torso 6%, and so on. We can also use activation distribution, and we can also visualize which filter is activated by which part object in the input maze. So now we can compute rho I and rho I hat. Rho I is given by the element-wise multiplication of the weight V of the chosen node V per xi, and the rho I hat is given by A per rho I just computed. The dth element of rho I denotes the contribution of to the CN prediction made by the dth filter. The matrix A, that is the same matrix that we mentioned at the end of the algorithm, is a binary matrix 0 or 0, 1 with dimension m per d, and d is the number of filters, as we already said, and m instead is the part number. This matrix is useful because assigns filter in the top conv layer with a specific object part. So if the rho I bth element is positive, this means that the bth filter makes a positive contribution. If it is negative, this makes a negative contribution. The mth element of the rho I hat instead measures the contribution of the mth part. So now, at the end of the paper is evaluated. We will not enter inside the formulas of the evaluation metrics proposed in the paper, neither in the results, because the most important thing here was the method. In the paper, the results are not discussed so accurately, so it's not useful also entering the metrics deeply. First matrix is about this fact, that is the accuracy of the estimated rationale of the prediction. And the first matrix is the errors of object part contribution to the CNN prediction. So this is given by this formula, and it is given by y minus y I hat. Y denotes the original CNN prediction. Instead, y I hat is the output when we remove the neural activations from feature maps corresponding to the ith part. Then another measure for this kind of objective is the fitness of contribution distributions. This compares the ground truth contribution distribution over different filters in the top layer with the estimated contribution of these filters during the prediction process. Then, another important thing is the information loss of using the decision tree to represent a CNN. This is easily evaluated because we have the classification accuracy, and indeed we have the h hat xi that denotes the prediction of yi based on the best child in the secondary layer, and therefore we can compare this classification with that of the CNN. And finally we have the prediction error that measures the error of the estimated value xi with respect to the true value yi. So we arrived at the end of our presentation, and we use a decision tree to explain a CNN prediction at a semantic level in this paper, and the decision tree encodes the decision modes of the CNN as a quantitative rationale for each CNN prediction. This method does not need any annotation of object parts or textures in training images to guide learning the CNN. That is an important thing. We arrived at the end. Thank you very much for the attention.